Hi everybody. Today we're going to look at actually what happens when we have exponential and log functions. So an exponential function is a function of the form f of x equals a to the power of x. So it's basically where we have the x in the power. So that's why we call it an exponential function. So we will talk about what happens if a is 0, a is less than 0, but for the moment we're going to consider two cases of a more than 1 and a less than 1. And these have very set, the shapes are very similar. Well, yeah, for different values of a greater than 1. So they have these set properties given alongside here, so they don't have any stationary points or points of inflection, so that means that f dash of x doesn't equal 0, and nor does f double dash of x equal 0. They're increasing, so you can see the function's always going up, which means that the derivative would always be positive for all x in the real numbers. The x-axis is a horizontal asymptote, so as x goes to negative infinity, we can see that the function is approaching 0. And then there are no vertical asymptotes, so there's no point where the function doesn't exist, creating a vertical asymptote. Now they're also one-to-one functions, which means that if I draw a horizontal line, it only intersects the graph once, so it will never come back down. And we can see that that's happening here, that wherever I draw a horizontal line, there's only one intercept with the function. They pass through the point 0, 1, so this y-intercept here is always going to be 0, 1, regardless of the value of a. Because if you think about it, if x is 0, I have a to the power of 0, which is 1. And the gradient of g of x as at this y-intercept increases as the value of a increases. We'll talk about that one in more detail later. So the domain of the function, well, the function exists at all real numbers. If I raise any positive number to a power, whether that power is positive or negative, it's going to exist. So the domain is x in the reals. Now the range of the function, well, we said that the x-axis is a asymptote, which means that we can see from the function that it's existing only above the x-axis. So it's the values of y such that y is greater than 0. It's not equal to 0 because x equals 0, the x-axis is a horizontal asymptote, so the function never touches that. The functions are called exponential growth functions because you can see that as we move to the right, the value of the function is growing. Okay, all right. Now, what about if a is between 0 and 1? Well, it changes. And it's basically just the reflection of the previous function in the y-axis. So again, there's no turning point. So again, the derivative and the second derivative is not equal to 0, which means there are also no inflection points. They're decreasing this time. The x-axis is still a horizontal asymptote. There are no vertical asymptotes. They're one-to-one, and they pass through that point 0, 1. All the same things apply, apart from the fact that instead of going up, it's going down. And so these are called exponential decay functions. So there's the decay or decreasing going on. Okay. Now, if we think about it for a moment, sorry, let me just get rid of that. I said that these are the reflection of the previous ones in the y-axis. So let's think about why. Let's say I had 1 on a to the power of x, where a is greater than 1. Well, this would be a to the minus 1 all to the power of x. And so it would be a to the power of minus x. And so then if I have f of x equal to a to the power of x, then 1 on a to the power of x equals a to the negative x, and so it's f of negative x. So f of x is a to the x, 1 on a to the x is just f of negative x, and f of x and f of negative x, if you recall what we did on transformations, are reflections of each other in the y-axis. Now, sometimes as the power, we don't use a whole number. So, a could be a positive number, and so it could be 2 to the power of x, or 3 to the power of x, or 4 to the power of x. Sometimes we choose a different number, and it's the irrational number e. You may not be familiar with that, but it's like pi. So pi is 3.14159, and so it goes on. E is similar. It's an irrational number that goes on forever, and it starts as 2.71828, and then it goes on forever. Now, why we actually use e and are interested in e to the power of x, we will discuss later. But for the moment, sometimes we talk about the function f of x equals e to the power of x. Now, because we're interested in this, we also can have log of base e, and we write that as ln. So log of base e is equivalent to ln. They're the same thing. Okay, so if I had f of x is equal to a to the power of x, let's find the inverse function. So I would start with y equals a to the power of x, and then I would switch x and y. So the inverse would be x is equal to a to the power of y, and then I want to rearrange that for y. So let's take the log of base a of both sides. So that we log of base a of x is equal to log of base a of a to the power of y. And so I can say, okay, well that's log of base a of x, and the log of a and the a kind of negate each other, and so y is equal to log of base a of x, and so my inverse function is log of base a of x. So a to the power of x and log of base a of x are inverse functions. So let's look at the logarithmic function f of x equals log of a of x. And we're only going to consider situations where a is greater than 1. And it has some key properties. Firstly, it asymptotes to the y-axis because log of base a of 0 does not exist. So what that means is that x equals 0 is a vertical asymptote. If you think about it, like why does log of base a of 0 not exist? Well, remember, a log is giving us a power, and there's no power of a real number that will give us 0. So if you think about 2 to any power, 2 to the power of 1 gives us 2, 2 to the power of 0 gives us 1, 2 to the power of minus 1 gives us a half, and then it's a quarter, and so on. So nothing, I cannot find a power that will make such that I raise 2 to that power to give me 0. There is no power such that 2 to the power gives us 0. It always has an x-intercept at 1. So that's because log of any base of 1 gives us 0, because a to any power gives us 1. It's always increasing, which means that the derivative will be greater than 0 for all x in the rules, for every value of x. Well, actually, not every value of x, because it doesn't exist past 0, so it's just for x greater than 0. has no stationary or inflection points, which means that the derivative and second derivative aren't equal to 0 at any point. Doesn't have a horizontal asymptote. Because it goes up and it seems to flatten out very quickly, it can be easy to think it does have a horizontal asymptote, but there's no asymptote. There's no horizontal asymptote on log function. And again, like the exponential function, it's one-to-one. And so we can see that by drawing the vertical lines there. So the domain of the function, well, log of 0 doesn't give us anything. Log of a negative number doesn't give us anything, because again, I can't raise 2 to any power, so it equals something negative. So the domain of the function is just x, such that x is greater than 0. Just the values greater than 0. The range of the function is the values of y. Well, all of them exist, because we have negative powers and positive powers. So it's y is in the real numbers, any real number. Okay, now we've touched on the log of base e. So that's log of base e of x, or another way we can write it is ln of x. Now, the other thing we want to look at is we want to think, well, yes, we can have the standard functions, but we can also have transformations. And so I want to remind you about the transformations in these functions. So first of all, D is kind of the easy one. D is the vertical translation, moves the graph up or down. K is vertical dilation, so it stretches or compresses the graph vertically. It either stretches out away from the x-axis, or it compresses it towards the x-axis. So that's K. Now B is horizontal dilation, so it stretches it either away from the y-axis or compresses it towards the y-axis. So it's horizontal translation by a that's wrong. It's horizontal dilation by a factor of 1 on B. So vertical translation up or down by D, and vertical dilation by a factor of K. It's very important that when you're describing the transformations that you actually give the factor. And then C, if it's in the form x takes C, well, that's horizontal translation by a factor of C. Okay, so those are some important things we're going to need to look at in this case. Now we'll leave it there and we'll go through the examples in class, but that sort of gets the actual content, the concepts, but then we'll apply them in class.